Hello, this is Lex Berman, and this will be the second of two videos on georeferencing historical maps. In the first video, I showed an example of using QGIS 3.16 and the georeferencer tool. In this video, I'll talk more about strategies and approaches to your georeferencing task. So when you do georeferencing, as you know, you have to go through several steps to get from your historical map, which is going to be a scanned image, a raster image, and you have to use a geometric transformation in order to transform the image shape to a real-world coordinate system. And of course, the way you do that is to add ground control points, and those points then are hooked to a reference map, which is in real-world coordinates. Even after the transformation process is done, then it gets resampled into a new image. And there are errors that can creep in at every point of this process, but basically when you go into georeferencing for the first time, you want to know which transformation to pick, because you'll have a choice of polynomials and affine transformations and thin plate spline transformations, and it's hard to know which one is appropriate for your task. Essentially, a first order transformation only rotates it or moves it to one side or up or down. It doesn't actually stretch the shape or distort it differently from the original image. It just reorients it or moves it, scales it. The second order affine transformation, or the polynomial 2 transformation, that actually starts moving each pixel of the map around using a geometric algorithm. And then it can get even more advanced using third order polynomial calculations. However, I have found, and it's generally true, that the thin plate spline is going to work for historical scanned maps. Now, why is that? Well, a number of reasons, one of which is that we don't always know the original projection. Another is that there could be different kinds of errors that I'll talk about that get introduced that you need to correct for. And what thin plate spline essentially does is it moves it the least that it has to. So depending where your control points are picked, it will warp the image around those points, to the minimum extent that it can fit the real world coordinates without warping the whole image too much. In that way, it generally works pretty well for our historical maps. The next question you're probably going to ask is, how many points do I keep adding in? Well, there's a minimum number of points, obviously. There's no way you could use less than 3. And generally speaking, in any second order transformation, you're going to need 6, and so on. However, it's been recommended that you use double that. So, double the minimum that you could get away with. So you're saying say 10 to 12 points. And I think 10 to 12 points is a good minimum for any map, although the examples I'll show you probably use a few less, probably 8 points or something like that. Now, what about the actual settings when you go into QGIS and start messing with this? Well, the georeferencer tool, shown here on the left, has a window where the map gets loaded, and then it'll have a list at the bottom, or you can show a list at the bottom of all the ground control points that are being added to the map as you pick them and relate them to places on the real-world map. Now, in the transformation settings of the georeferencer, you're going to have to choose one of these transformations, as I said, in order to do the georeferencing process. And also you have to choose a resampling method, which is essentially the math. There's nearest neighbor, which is just simply which is the nearest pixel that would overlap in the real world to the one that you've linked together. Then there's other factors. You can go the 4 nearest, an average of the 4 nearest, or you can go cubic and get an average of the 16 nearest pixels and so on. but nearest neighbor will probably work for us. You want to give the output raster a different name so you don't overwrite anything by accident like your original image. And save the GCP points, why not? You might as well save them to a separate file in the process of doing this, and that way you have a record of what you did. And also you can check off use 0 for transparency when needed, because that'll prevent a big black collar from showing up, although in some of the examples I'll show I didn't do that, so you can see the difference. Now, after you've run, actually I should point out that in the upper toolbar of the georeferencer, you'll know that there are different ways of adding control points or deleting them, and zooming in and out and panning around the image. But there's also the green run button, which essentially says, run this transformation that I've set in the parameters. So it's not, even if you select your parameters and hit OK, it doesn't actually do anything until you hit that run button. And then you'll see down here in the bottom list of ground control points where it says residual pixels. What that means is the residual error in the units of pixels. And it says 0000 because it hasn't been run against anything and has no way of checking the real world coordinates to know what kind of error is involved. So once you actually hit that run button, then the residual errors will start showing up. And you can add and remove control points or edit them and then rerun the same transformation, and you will see these residual error numbers change. And what does it essentially mean? Well, the closer to 0, the closer to an exact match it is. And if it's like 1 or 3, this is like 1 or 3 pixels error. Now, depending on the scale of the map that you used and the resolution that it was scanned at, 1 to 3 pixels could be 5 to 10 kilometers, and it really is in this case. So how do you choose where to put the ground control points on your map? Well, the general rule of thumb is try to distribute them around the full shape and extent of the map. In this case, it's Japan, so it's sort of an elongated shape, so you want it, sort of through the middle, but also out towards the ends. And you could use the minimum here. The 6 points is just a bare minimum. And, you can see how the ground control points after the transformation was run has warped this image to fit the real world. If you add vectors, in this case the natural earth free vectors for the world, ADM level 1, so it shows the first level administrative units underneath the countries. And you can see that the blue lines in some cases snap pretty well, and then towards the edges there starts to be a drift from the border in the image and the vector border. So what distance is that? Well, you can go in and measure it using some of these tools. I'll show you how to use Map Analyst, and you can get an idea of that. Now, this is what happens. By the way, this was the thin plate spline transformation. The same tick points, same map using the polynomial 2. You end up with this really weirdly warped situation. And it probably has to do more with the fact that the original map, was not in it was in a very customized kind of projection, is what I'm saying. Or there were inherent warpage in it that, simply is not going to work with polynomial 2. Here's another example. Looking at historic map of Prague from this Austrian-Hungarian military map from 1906. And this is the Prague region of Bohemia, and it's tight on Prague city over here where the cluster of points are, and then I've chosen a few more towards the boundaries of the map to try to improve the georeferencing. And this is thin plate spline with the blue roads, and I had red buildings. This is using OpenStreetMap vector map for my georeferencing base map. And they have very accurate roads and very accurate building footprints, which are super useful if you're going to do any kind of urban features on the map. However, if you tried once again to use the polynomial 2, although it worked kind of well within the city itself, but it just introduced all kinds of weird distortions the further you went out. Now, what kind of distortions are we talking about that can happen when we're doing all this? Well, The original surveying and cartography could have errors. Even the instruments could have tiny errors. The printing process, of course, printing something on a flat plate, it could curve, the ink could not spread properly. And then the object itself over time. I mean, we're talking about historic maps, so they're going to have folds, they're going to get wet and dry up, they're going to shrink, and the condition of the map could have, different kinds of problems, ink rubbing off and so on, over prints. And then there's, later on, after the historic object itself, then we introduce whole new levels of problems when we scan it or photograph it, and then that, was the map perfectly flat on the surface, and did the scanner optical process work at a consistent speed enough to not introduce any tiny little stretching or error of the image. And then, of course, when we go in to do the georeferencing, our choice of ground control points has to be absolutely as accurate as we can possibly get it in both the historical map and in whatever we're using for our ground control reference map. So, depending on the scale of your map, that may be impossible. You may never be able to get more accurate than a kilometer. For an old map at 1 to 20 million scale or something, it's just simply not going to be possible. But you do the best you can. Then there are transformation issues, as I just mentioned. If you don't have to hook it to the original projection. In fact, I would recommend do your georeferencing against a modern WGS 84 lat long, coordinate reference system. You don't want to introduce a whole bunch of problems by trying to guess original projections and not getting them quite right, or knowing the central meridian exactly and so on. It's just easier to georeference it to your modern base maps. And finally, that last step where after the transformation geometry is calculated, then it gets pushed out and resampled to a new image, and that can introduce errors too, depending on the level of resolution and a number of other factors. So what does that mean? Well, let's look at this tool that we have where we can use Map Analyst, which is a freeware, that creates distortion grids, and the distortion grids allow us to analyze the warping of the image a little bit. It also provides some other really useful information about how the georeferencing worked when it was done with the transformation that you chose. Now, one warning here is that it requires an image with the DPI, the resolution, embedded in the file itself, which by default happens in a PNG file, and it could be in a GeoTIFF. However, the GeoTIFF file size could be very, very large. So just to tell you my workflow, I generally will export the GeoTIFF from QGIS at full resolution, whatever I can possibly get to get the maximum quality of the georeferencing going on. And then I will load that GeoTIFF into an image processing software. I use another freeware called GIMP, and I'll export that to the PNG file. That will have the embedded information I need to bring the old map image, they call it the old map image, into Map Analyst. So what does Map Analyst do? Well, before we get there, let's look at a few examples of historic maps and what could go wrong. Like, you see all these folds in this old 1876 map of Central Asia done by the Russian explorer Przewalski. And if you go in and do a high resolution scan, which was done for this map, there were 11 different images originally as TIFFs, about 20 megabytes each. So you can get pretty accurate, but of course, once this was digitized and georeferenced and the planimetric error was measured, there were definitely, it'd be 10 kilometers off in places, which, considering that they were tramping over the mountains and deserts of Central Asia on camelback with their own, non-digital equipment in 1876, it's a pretty incredible map, and they're climbing up these passes at 4,000 meters, 5,000 meters. So this is a typical historic map case. What does it look like once you've got it georeferenced and put into the Map Analyst distortion grid? Well, you can see on the left the original old map image and where it was hooked to on the ground in the right image. And I just used a minimum number of points here, and you can see in the bottom right there's some useful information provided once you hit the compute button in the upper left. So basically you bring the map into here, you hit some more ground control points. You have to hit them over again in this case because the map image is in it says it's in meters, but it's basically measured in pixels, and it goes from the raster image, lower left corner, and it's not in the same units as the one that you would export from QGIS, so you have to do it over. Once you hit compute, after you've picked your ground control points and hit compute, it provides both a distortion grid and as well as ISO lines or other things. You can change the mesh size in the bottom left and then run it again. You also on the bottom right get useful stuff. It guesses the scale based on how it had to do the georeferencing. So it says this is a 1 to 2 million map. And it says what rotation from north does it have. It doesn't really have any. It's 2 true north. And what is the deviation? What is the basic planimetric deviation? Well, it says it's 35 kilometers. So I think that there are some errors that were introduced by the georeferencing points chosen in Map Analyst in this case. I don't think it's really that bad. How about the Japan highways example? Well, again, you see this huge fold in the middle and it's like warped probably with moisture. Plus, look, it's oriented right to left to fit into this rectangle. It's not really the real orientation of any projected, normal projection for Japan. So if you take your Japan case and stick it into the Map Analyst to get the distortion grid, I wanted to show you here that if it has less than say 75% accuracy, or if it's 75% uncertain, it will just gray out the grid and it won't even show you the lines. And you can set that threshold to 50% or whatever and change the way the distortion grid looks. You can also see sort of the mesh, the way it spreads out on the modern map, and it gives you an idea of where it's being distorted and in what way, And then of course you see the error down here says it's about 5 to 7 kilometers of error. And it also says, by the way, it's 20 degrees rotated, which we knew because it's really, the map has been rotated and unnaturally to fit into their cartography. Now, what about an unknown or customized projection? Now I'm going to run you straight into Map Analyst and show you how to do this. So let's see if we can get this up and running. Here's Map Analyst software. You want to create a new project, and then you want to so-called import an old map image. And the old map image I'm going to import is just going to be a ping, but it's going to be not the full resolution, so it'll load up in here in time. Now I'm going to want to re-pick some points here, and you need to know your geometry really well, your geography really well, in order to do this probably. Now, let's see, where are we? We're around Eastern Europe. Here's these tools up top. You have to pan around and find where you want to be. Here's Czech Republic right here. So we're actually basically just right around Prague, just right around in this tight little area here. And then you go to map and you pick a few points. Again, this image was knocked down in resolution so that it would load quickly as I'm giving you this demo, but there are identifiable features here. This bridge point at the northern edge of Old City of Prague is right here. It's a famous bridge. And then you need to link it. So when you choose each one of these, you need to establish a concrete link with a name. You could give it a serial number or whatever, but I like to put a name in. And then you need to reiterate this process for a minimum of 5 points. So that will take me a little while because I'm not that expert on the geography of Czech Republic, but enough so that it won't waste a whole lot of time. So here's Rostock right here, and Rostock right here. And give that a name, Rostock. Okay. And then we'll just quickly try to go over to, say, Brandeis up here. which is, where is Brandeis? Where are we? Brandeis, somewhere around here. Try to find it quickly. Thought it would be easy to find, but not always. Elba. I thought I had Brandeis right there, but not. Hang on. Rostock, Prague, and here it is, Brandeis, right here. Okay. All right, and then we'll go over to the this map here. We'll just find the equivalent spot, which has the convenience of relabeling in the modern map. It makes it a lot easier. Okay, so in Brandeis we can actually get a couple of local places like this Popovich here, which is right down. You can see the old stream and ends right here. And that's a very characteristic location for me to add. Okay, Popovich. Okay. And then I'll just put one right here for convenience, Drewitz, just to keep things moving. You really only need 5 points. Okay, now we'll go down to the bottom and we really only need one more. And just cruise down here to the lower right. Try to get something towards the edge of the screen. Here's this Hradschin, and we can just grab that and Valley, and it should be somewhere right under here, and there it is right here. Okay, so we'll add that, Hradschin and Hradschin. Yeah, right about here. Okay, so now we should have the adequate number of points. Now, see this mesh size is 5,000 meters. We can go ahead and run that. And we need to set the, it will prompt us to set the transformation settings. No, it didn't. We can go back and set it. Well, it'll be Helmert. But let's see, it says down here, Helmert, 4 parameters, analyze transformation. You can pick your transformation here. I think that's fine. But notice the distortion grid is quite large. So what if we changed it to 1,000 meters? 1,000. Okay, and then we run it. And now you see that it looks like this. And these are the uncertain areas. So it really has quite a lot of uncertainty. And then you can compare it with the real world on the right. And this is basically how Map Analyst works. Now, at the bottom right, it's also giving us the guessed scale, 1 to 200,000, a rotation of 4 degrees from the north, and a standard deviation of about 1.8 kilometers to 2.5 kilometers. So, you know, how good can you get in terms of your georeferencing? Well, you could add a bunch more points, you could get a lot more accurate, but there's limitations to the resolution of the map itself and the other problems that I mentioned. So this is the presentation for today, and I hope that you learned a little bit more about strategies and analytical tools for working with your historical maps, georeferencing them, picking different transformations, setting your ground control points, and having some way of analyzing or looking at the results. So thanks a lot for joining me, and my best regards to everyone at the Institute for Transnational and Spatial History at the University of St. Andrews.